An exponential equation is an equation in which the variable we want to solve for is up in the exponent. There's two main kinds. The first is one in which both sides of the equal sign may be written with a common base. Here I have a couple of examples. In this first one, on the left-hand side, I've got something in base 2, and on the right-hand side, 4. We know that 4 can be rewritten as 2 to the power of 2. Now that I've got both sides of the equal sign with the exact same base, I can simply set the exponents equal to each other. That's a property of exponents. Now I've got this simple linear equation to solve. All I have to do is subtract 3 on that side, and I've isolated for x. This one's a little bit more complicated, but the idea is the same. This is 3, 27, 9. All of those numbers may be rewritten in base 3. 27 is 3 to the power of 3. 9 is 3 to the power of 2. Now that I've rewritten everything in base 3, I'm going to use my exponent laws to simplify this right-hand side. Remember that if you're multiplying two things with a common base, we can simply add the exponents. And recall that if you've got something raised to an exponent and then another exponent, we need to multiply the exponents. I have to multiply these two things and add it to there. That results in this. Now we've got 3 all to the power of 3 plus 2 times 2x plus 1. Just as before, common base, one single exponent, a big one. We can set these equal to each other, and now it's a linear equation. Distributing and isolating for x, we result in x equals -5/3. Sometimes we can't make a common base. 2 to the power of something will never be 17 unless we use decimals, and we don't want to do that. We have to use logarithms. Remember, one of the laws of logarithms from earlier was that if I take logarithm of something with an exponent, the exponent comes down in front as multiplication. And a property of equations is if I do the same thing to both sides of an equation, my equation is still okay, it's still balanced. So I'm going to take log of both sides so that this exponent comes down, and now it's multiplied by log of 2. Remember, log of 2, log of 17, these are just numbers your calculator can give you, so think of them as just numbers. That means I can divide both sides of my equation by log of 2, whatever that may be. If we put log 17 over log 2 into our calculator, we'll get approximately 4.1. It's a good idea to check your answer. We know that 2 to the power of 4 is 16, so it makes sense that 2 to the power of 4.1 would be a little bit more 17. This one's very similar. The difference is we've got this binomial as an exponent, but the process is the same. Again, I can't write this in base 3. I have no choice but to use logarithms. Let's take log of both sides so that my exponent comes down in front. Once again, I want to get rid of this log 3 and isolate for x. Log 3 is just a number your calculator can give you, so I can divide both sides by log of 3. Log 50 divided by log 3, once again, put that in your calculator, you'll get approximately 3.6. And finally, so that I get x isolated all on its own, I want to add 2 on this side, and the final answer is 5.6. Now let's solve some logarithmic equations. There are also two main kinds of logarithmic equations. Similar to exponential equations, some have a common base on both sides of the equal sign. Same property holds. If I have log base b of x is equal to log base b of y, it only makes sense that these two things must be equal to each other. So here's an example. If we look at both sides of this equal sign, I've got two logarithms and they're both base 5. Therefore, it follows that this has to be equal to this in order for left side to equal right side. So I set this argument equal to that argument. Collecting like terms and isolating for x gives me the result x equals to 4. In the second example, we're going to end up with one that doesn't work. So let's walk through it. First off, I have two logarithms on this side, both base 3. I no longer have one logarithm equal to another logarithm like I had in the first example, so first thing I have to do is simplify this, turn two logs into one using the laws of logarithms we've learned. They're both base 3, so I can multiply the arguments into 1. Now that I've got one log base 3 on this side and one log base 3 on that side, I can set the arguments equal to each other. Once again, we've got a linear equation we can solve. Distribute, collect like terms, isolate for x. My final answer is -7. We have to check our answer. If I go back to the beginning and I try plugging -7 into either one of these, you'll notice I get negative arguments, and that's not okay. We don't want that. Here I'm going to get -6, here I'm going to get -12. Therefore, this is not an answer. We say that it's inadmissible or extraneous, and this has no solution. We can also solve logarithmic equations by rewriting the logarithmic equation back in exponential form. So we're back to this. If y equals log b of x, we know that we can rewrite this using exponents by saying base to that exponent equals to that. That's the very definition of a logarithm. So in this example, I've got base 5 over here. Here's my argument. If I want to rewrite this in exponential form, it's going to be 5 raised to this power equals to the argument. And once again, a simple linear equation that we can solve. 5 squared is just 25. Collecting like terms, isolating for x, I get 11. And don't forget, check if it's an admissible root or an inadmissible root. Once I put 11 back in here, I would get 22 plus 3 is 25, and that's okay. And some applications of exponential and logarithmic functions. These should be familiar from previous years. Exponential growth generally is given by this formula. Your base here is going to end up being some number greater than 1. When the base of an exponential function is greater than 1, it is increasing. So this is the rate of growth, this is the amount that you start with, this is the time gone by, and that will be the final amount you're left with. This is exponential decay, something that is decreasing. If you have r, some rate of decay, we can find the base by taking 1, take away r. Now your base is going to be less than 1. When your base is less than 1, you've got a decreasing function. That models exponential decay. Two examples of growth and decay. Half-life is a common one used in science. Half-life is how long it takes for something to halve. Given the half-life, this formula will tell us the amount of some substance given the starting amount, time gone by, and the half-life of that substance. Doubling time is a specific example of exponential growth. Once again, starting amount, future amount, time gone by, and how long it takes for that thing to double. So an example, some substance has a half-life of 12 hours, i.e. it takes 12 hours to have half as much of it. We begin with 12 grams of this substance. How long until we've got 2 grams of this substance? So I'm going to use the half-life formula. I'm given the starting amount and the ending amount and my half-life. I've got those in there. Now I'm solving for t, which is in my exponent. This is an exponential equation. So first I'm going to simplify the right-hand side of this equation by dividing both sides by 12. I end up with 2 over 12 over here. Now in order to bring this t over 12 down, we learned how to do this earlier, take log of both sides. When I take log of both sides of an equation, I can bring down an exponent and multiply it by log of a half. And lastly, I want to isolate for t, so I want to divide both sides of the equation by log of 1/2 so that that's gone. And now I've got that t divided by 12 is approximately 2.58. And finally, I want to just have t on its own, so we have to multiply that side of the equation by 12. And the final answer is approximately 31 hours. After 31 hours, this substance will have gone from 12 grams down to 2 grams. On to logarithmic scales. Logarithmic scales are useful when we're dealing with large numbers. You may have noticed that when you take log of large numbers, it turns into smaller numbers. Some common applications are the Richter scale, you've probably heard of that, it's how we measure earthquake magnitudes, and loudness, decibels. When something is in a logarithmic scale, an increase of 1 on the scale is actually an increase of a factor of 10. An increase of 1 is 10, an increase of 2 would be 100 times greater, 3, 1,000, and so on. So for example, if a magnitude registers 7 on the Richter scale, and some other earthquake registers 5 on the logarithmic scale, because their magnitudes differ by 2, this one's actually 100 times as intense as that one. Differ by 2, and 10 to the 2, 100 times as intense. Another common example that we use logarithms to deal with large numbers is loudness. You may have heard of decibels. A sound that is 68 decibels will be 10 times as intense, will sound 10 times as intense as a sound that is 58 decibels. Now these differ by 10. The reason why it's only an increase of 10 and not an increase of 10 to the 10 is because we have to convert these to bells. The prefix deci means 10. 68 decibels means 6.8 bells, and 58 decibels means 5.8 bells. So in order to compare them on the logarithmic scale, we actually have to convert them into bells. When we do that, we notice that they differ by only 1, 6.8 bells versus 5.8 bells. Because it's an increase of 1 on the logarithmic scale, this is actually 10 times louder, 10 to the 1 times louder than that one.